In this lesson, we will study compound interest. We'll look at it from the perspective of putting money into some type of a bank account. So first, a definition. Compound interest is interest earned on the original principal, the amount that you invest, as well as any accumulated interest previously earned. This will be different than simple interest. For simple interest, as each year passes, you always earn the same amount of interest. With compound interest, the amount of interest you earn over time will grow. To explain how this works and to derive a formula, let's look at example 1. So this says, suppose you invest an initial amount of $1,000 into an account that earns 4% annual interest. What this means is $1,000 is the principal amount. That's the amount you first invest. And the interest rate is R%, which I'll call 4%. When we say 4% annual interest, we mean after a single year, this percent is applied to the amount of money that you invested to determine the interest that you have earned. And you do this once. And for that reason, we say it's compounded. The interest is compounded once per year. Now the question is, how much money will be in the account after 1 year? You start with $1,000. After a year, how much money should you have? If you remember, the way this works is you would take your $1,000 and you would multiply it by 4%. And when you do that, we can do this in a calculator. We get 40, which is $40. That's the amount of interest that you earned. Now the balance in the account is going to be $1,000 that you started with, plus the $40 you earned. So after a year, you have $1,040. Great. If you remember, you can do this in a single step. So instead of doing this in 2 steps, you can instead say, take 1,000 and multiply it by 1.04, not 0.04. Putting this 1 here will add the 1,000 back in for you automatically. This will be nice for this type of work. I'm going to check this in my calculator, but we get $1,040. This is the balance after 1 year. Okay, no problem. How much money is going to be in the account after 2 years? What we're going to do is we're going to take this 4% annual interest, but we're not going to apply it to the original $1,000. Instead, we're going to apply it to the actual new balance of the account. Going back to the definition of compound interest, that's what it means to say we apply the interest to any accumulated interest previously earned. So you're not just earning 4% off of 1,000, but you're earning 4% off of $1,040. So for the second year, you're going to take 1.04, but you're going to multiply it to 1,040, which is the balance after the next year. So for this reason, the new balance after 2 years won't be $1,080. Instead, I'll check this on my calculator. The new balance in the account is $1,081.60. So this is the balance after 2 years. This is why compound interest grows faster than simple interest. It's because you're applying some interest rate not to just the original balance, but always the balance of the account at that time. So it grew by $40, then it grew by $41.60, which is a little bit faster. The next part asks to figure out the balance in the account after 10 years. And really, you could just repeat this process 10 times. You could take this value and multiply it by 1.04, get a new balance, do that again, do it again, until you've done this a total of 10 times. But it turns out there is a faster way to do this by using a single formula. To explain how this works, let's look at our very first step to find the balance of the account after 1 year. What did we do? We took $1,000, we multiplied it by 1.04, and then we got our value of 1,040. No problem. We applied this once, meaning it's to the power of 1. Then we took this amount and multiplied by 1.04 again. You could really interpret this as start with $1,000, multiply it by 1.04 once, but for the next year, you can multiply by 1.04 a second time. This part right here is equal to 1,040, and here you're multiplying by 1.04 again. What is a faster way to write 1.04 times 1.04 using exponents? That is 1,000 times 1.04 squared. So if you want the balance after 1 year, you would just put a 1 in this exponent. If you want the balance after 2 years, you can put a 2 in this exponent. What if you wanted the balance after 3 years? This trend continues. You would take 1,000, you'd multiply it by 1.04 to the power of 3. I'm going to type that right into my calculator. So 1,000, 1.04 raised to the power of 3. I'll round to the nearest hundredth, which is the nearest cent. That's $1,124.86. So this is much faster, especially in a calculator. You can just change this number to wherever you want to determine the balance of the account after any number of years. So what do you do for 10 years? Kind of running out of space, but I'll put this off to the right. So for 10 years, the balance is 1,000 times 1.04 to the power of 10. This is not to be done by hand. This can be done right in a calculator. I'm entering in this now. Rounded to the nearest hundred, I get $1,480.24. I'll now state the formula for compound interest if you're compounding once per year. I'll call it A. It's equal to the principal. In our case, it was 1,000. And you multiply that 1 plus the interest rate as a decimal to the power of t, where t is the number of years if r is an annual interest rate. So looking down here, r was equal to 0.04. If you add 1 to it, you get 1.04. The principal was 1,000, so you can put 1,000 right here. The amount of time in years, in this case, was 10, so we put 10 in place of t. We can now use this formula for if you're compounding some annual interest rate once per year, you can determine the balance of any account. In this example, it also asks how much interest is earned in each case. And I stated it for the first two. After 1 year, you earned $40 interest. After 2 years, it was $81.60. After 10 years, how much interest was earned? What you would do is you would take your initial amount, which was $1,000, and you're subtracting that from the value of the account, which is, in this case, $1,480.24. So here the interest earned is $480.24. So in 10 years, this is how much money you actually earned in terms of interest. Now let's discuss a general formula for compound interest. I'll again let P represent the principal, that's the amount that we invest. R is going to be the given annual interest rate in decimal form. But what's new is N is going to represent the number of times that the interest is compounded over the course of a year. So in the previous example, N was equal to 1. We applied the interest rate just once. But you could also apply the interest rate twice, and that would be semi-annually. That would be N is equal to 2. You could apply the interest quarterly, 4 times per year. That's N is equal to 4. Or perhaps even monthly, so N would be equal to 12. How will this change the formula that was in the previous example? So A is going to represent the balance of the account. The formula, it looks very similar to the formula in the previous example. It still is the principal, and it's multiplied by 1 plus the annual interest rate in decimal form, but you split it up into the number of times that you're compounding. So this time, R is divided by N. In the exponent, last time it was just T, but here you multiply T by N. This is the general formula for compound interest if you're compounding N times per year. Let's see how this works. In example 2, it says, suppose you invest an initial amount of $1,000, so that's your principal, and it goes into an account that earns a 4% annual interest rate, but this time, it's not compounded annually, it is compounded quarterly. if I write down this information, again, our principal is $1,000. The interest rate as a percent is 0.04. That's not different. But this time, n is equal to 4. Essentially, what we do is we take this interest rate, we divide it into 4 equal parts, and apply each of those to $1,000 at 4 equal intervals over the course of a year. So that's important. We're taking 0.04 and we're dividing it by 4, and that is 0.01. And that's what this part of the formula says. It says you're applying this interest rate, but you're doing it 4 times, so you have to split it up into that many parts. So how much money is in the account after 1 year? It works the same way. After 1 year, you would start with your $1,000, and you would apply 1% interest at some point. That'd be after the first quarter. So the new balance of the account is 1.01. So you applied 1% of the 4% interest after the first quarter. This is the new balance of the account. You now apply 1% to this after the second quarter. So we multiply by 1.01 again. And again, we have this new balance in the account. This is after the second quarter. How much money is in the account after the third quarter? Well, you'd multiply by 1.01 one more time. And after the course of the entire year, after the fourth quarter, you would multiply by 1% yet again. And we have this expression here. If you multiply all this out, this will tell you the balance of the account after 1 year. So just to reiterate, we had 4% that was split into 4 equal parts. So really we were applying 1% to determine the balance. But you have to do that a total of 4 times throughout the year. What's a faster way to write 1.01 multiplied to itself 4 times? That's 1.01 to the power of 4. So a faster way to write this would be 1,000 times 1.01 to the power of 4. It's this thing that I would type into a calculator to figure out my answer. Notice this is the formula. So we have 4% that we divide into 4 equal parts. So really we had 1.01. This was after the course of 1 year, so t is equal to 1. But you really want 4 up here instead of 1. Therefore, you put 4 times t, and 4 times 1 is 4. The principal is not different. That is 1,000. I'm going to type this into my calculator and see what I get. That's 1,000 times 1.01 to the power of 4. And the balance in the account is $1,040.60. If you compare compounding the interest annually to compounding it quarterly, it's better if you compound it quarterly. In fact, the more times you compound, the more money you are going to make if you're working off of the same interest rate. Okay, how much money is in the account after 2 years? So for 2 years, we would take this value and we would do this process again. So we're going to take this and multiply it by another 1.01, a total of 4 times. For efficiency, I'll say, well, the balance in the account is 1.01 to the 4th power times 1,000. This is the balance after a single year. You're doing this again to figure out the balance of the account after 2 years. So you're multiplying by another 1.01 to the power of 4. When your bases are the same, you can add the exponents, and that gives you 8. So that's 1,000 times 1.01 to the power of 8. This is 4 times 2, and that's why we need the product like this in our exponent. I can instantly type this into my calculator, and the value I get, the balance of the account, after a total of 2 years is $1,082.86. So here the account is growing faster and faster and faster. Furthermore, if we are compounding quarterly, that's better than compounding annually. And finally, what is the balance in the account after 10 years? We're essentially taking this formula and we're putting 10 in place of t, and n is equal to 4. We just have to know what the exponent is going to be on that number. So for 10 years, that is 1,000 times 1.01 to the power of n is equal to 4, that does not change, but what does change is what we put in place of t. In this case, it's 10. So this is 1,000 times 1.01 to the power of 40. And I'm going to do this in my calculator. I get $1,488.86. This question also asks for the amount of interest earned in each of these cases. That'll be the difference of each of these numbers from $1,000. So I'll write it directly next to all of those. For here, after 1 year, the interest is $40.60. Here, after 2 years, the interest is $82.86. And this last part here, the interest is $488.86. In example 3, suppose you invest an initial amount of $5,000 into an account that earns 6% annual interest that's compounded monthly. How much money will be in the account after 10 years? And we will round our answers to the nearest cent. So just to state the formula that we have, A is equal to the principal times 1 plus R divided by N to the power of NT. Here, A is the value of the account after some amount of time, P is the principal, R is the annual interest rate expressed as a decimal, N is the number of times that you compound, and T is the duration of time. So by looking through this problem, the principal is $5,000. The annual interest rate expressed as a decimal is 0.06. The number of times that we are compounding is monthly, so that means a total of 12 times. And T is equal to 10, and that's written in years, which is good because that has to match up with an annual interest rate. So let's see what we have. A is equal to 5,000 times 1 plus 0.06 divided by 12, all to the power of 12 times 10. If we simplify this, whatever it equals is the balance of the account after 10 years. So I'm getting out my calculator to simplify this a little bit. So I'll start with the 6% divided by 12. If I look at that, okay, this is really 5,000. 1 plus 0.06 divided by 12 is 0.05. That's no surprise there, 0.005. And the exponent of 12 times 10 is 120. So the balance of the account is 5,000. Then we have 1.005 to the power of 120. I can now just simply enter this in and see what the value is. 5,000, 1.005 to the power of 120. This is equal to $9,096.98. So over the course of 10 years, with this annual interest rate compounded monthly, we almost doubled the initial investment. All right, so that's it for this problem. Okay, so at the top, I've written the formula for compound interest. Example 4 says, how much money should you invest into an account that earns 8% interest compounded semi-annually so that it will accumulate to $5,000 in 4 years? Now, if you think about what we're looking for here is, this $5,000 is not the principal. It's the amount that the balance will become after 4 years. That value is A, so A is equal to 5,000. And what we're looking for is how much money we should invest at the start. Well, that's the value of P. So for this problem, we don't know what the principal value is, but this is what we have to figure out. We can still use this formula to do that, even though P is not solved for by itself. We can do this by dividing both sides by this entire expression. If I take all this and divide it over here, we have solved for P. P is equal to A divided by 1 plus R over N to the power of NT. So by dividing this to the other side of the equation, we actually have the formula set up for us to use. A is equal to 5,000. R is equal to 8%, so really R is equal to 0.08. N is equal to 2 because we are compounding semi-annually. And T is equal to 4 because this should happen over the course of 4 years. I will take all this information, put it into this formula, simplify it to solve for P, and I'll use a calculator to help me do this. So P is equal to 5,000 divided by 1 plus 0.08 all over 2 to the power of 2 times t, which is 4. So if I go through each part of this, I'll leave the numerator alone, that's 5,000. If you divide 2 into 0.08, you get 0.04. So this is 1.04 to the power of 8. This is an expression you can type into a calculator. So if we do that, 5,000 divided by 1.04 to the power of 8, the value I get back is $3,653 and approximately 45 cents. This is the original principal, the amount that you need to invest under these conditions in order to end up with $5,000. Now that we've looked at the definition of compound interest in a few examples, how do you know what account is best to put your money in? So for example, you could compound at 4% interest 12 times a year, or at 5% interest for 4 times a year. They'll give you different amounts. How do you know which is best? And that's where the definition of effective annual yield comes into play. It takes all of the different types of accounts you could possibly have with compound interest and reduces them down to a single number that you can compare from account to account. So more formally, the effective annual yield is the simple interest rate that produces the same amount of money in an account after 1 year for some given compound interest rate. Here's that process outlined in 2 steps if you're looking to find the effective annual yield. What you do is, given your compound interest rate and your account information, find the value of that account after 1 year. Then what you can do is use the formula for simple interest to find the interest rate that will produce that same value. Recall that this was one of the definitions we had for simple interest. So effective annual yield is actually an interest rate, and it will be expressed in decimal form. In example 5, let's go over how we can compute this thing for this account. Suppose you invest $5,000 into an account that earns 4% interest compounded quarterly. Let's find the effective annual yield. Since we now have 2 different interest rates, the one from the account and the effective annual yield, we will call the one associated with the account the nominal rate. So step 1 is, let's find the value of the account after a single year. Now, if you remember how that formula worked, we took the principal amount, which is $5,000, and then we multiplied that by 1 plus, in this case, the nominal rate, 4% as a decimal, divided by the number of times that we're compounding, which is quarterly, so 4. And then we raise that to the power of 4 times 1. 4 for the number of times that we're compounding, and 1 for the value of the account after 1 year. The thing that we're going to set this equal to is this simple interest formula. The principal amount is going to be the same as this principal amount, so we can put $5,000 multiplied by 1 plus R. R is the thing we're solving for. In fact, this is the effective annual yield, and time is equal to 1 year, so I don't have to write anything at all for that. So the goal here is to find R. So just to reiterate, all of this stuff on the left side here, this is the formula for compound interest. The nominal rate is 4% divided by 4 because we're compounding 4 times, raised to the power of 4 times 1, where this 1 is the value of the account after 1 year. This side is the formula for simple interest. It's the same principal amount. Then we have 1 plus R, and this is the thing we're solving for. This will be the simple interest rate that produces the same amount of money if we were to compound for 1 year. Okay, let's simplify this. On the left, I can write this as 5,000 times 1 plus 0.01 to the power of 4. So 4 goes into this 0.01 times. 4 times 1 is 4. And on this side, I think I'll just leave it as 5,000 times 1 plus r. I'm noticing there's a 5,000 on both sides of my equation. I can divide 5,000 to both sides, or cancel it from both the left and the right side. Also, we have 1 plus 0.01. This is the same thing as 1.01. So this is 1.01 to the power of 4, and that's equal to 1 plus r. R is the thing we are solving for. Since I canceled the 5,000, I don't need these parentheses any longer, so I'll write 1.01 to the power of 4 is equal to 1 plus r. If the goal is to solve for r, we can subtract 1 from both sides of this equation, so I'll subtract it on the left and the right. This side I'll write as 1.01 to the power of 4 minus 1. And on the other side, we're left with r, since we're subtracting 1 from 1. And this is my effective annual yield. All I have to do is type this into a calculator and see what number that we get. Okay, that number is 0.040604 and so on, and that is equal to r. If we express this as a percent, we would move the decimal over 2 places. So this is, I'll continue that work over here. That is 4.06 approximately is equal to r. And if we round this to the nearest tenth, here's the tenth. This means it'll round up to 1. So approximately 4.1 is the effective annual yield. So to recap, what does this number actually mean? You could invest this money in 2 ways. You could either put it into this account that earns 4% interest compounded quarterly, and in 1 year, you'd have some amount of money. Or you could put it into a simple interest account with this interest rate, and you would end up with the same amount of money. Basically, both of these accounts would be the same thing because we set them equal to each other. The nice thing about this number here, the one that comes from the simple interest formula, is that simple interest has a simpler formula. Let's now use this definition to compare 2 different accounts. Before we look at example 6, let's state a general formula for the effective annual yield. And we'll switch things up just a little bit here. We're going to let r be the nominal rate expressed as a decimal, and n be the number of times this interest rate is compounded per year. The effective annual yield is going to be denoted by this capital Y, and the formula for it is as follows. It is 1 plus r, the nominal rate, divided by the number of times we're compounding, raised to the power of n, technically n times 1 because we only care about what happens after 1 year, and then we subtract the number 1. If you notice, this is exactly what we ended up with in the previous example. At the very end, when we solved for the effective annual yield, we had canceled the principal amount and basically just took this part of the exponential equation and subtracted 1 from it. I will use this formula in example 6 to compare 2 different accounts. So, in example 6, which account is a better investment? An account earning 8% interest compounded monthly, or an account earning 9% interest compounded annually? What we'll do is compare the effective annual yield for both, and whichever is bigger is the one that will make you more money. So let's start with the one here, the 8% interest compounded monthly. I'll compute this number for it. So for the 8% account, if we compute the effective annual yield, it is equal to 1 plus, here's 8% as a decimal, and we're considering it monthly, raised to the power of 12, and we're subtracting 1. I'm going to directly enter this entire expression into a calculator, and then we'll see what number we get for y. So I'm using the Desmos scientific calculator. So parentheses 1 plus 0.08, then divided by 12 creates a fraction. I push over, close the parentheses, and use the caret symbol to get an exponent of 12. I push over once to get out of the exponent, and I subtract 1. And the value for y that I get is, let's see, 0.0829995. And if you want to think of this as a percent, we can move this decimal point 2 places. And what we have is 8.29995%. So there we go. That is the effective annual yield. Now, if we do the same thing for the other account, that one was 9% interest. I put annually. I meant to put semi-annually, meaning twice a year, where n is equal to 2. With this correction, y, the effective annual yield, is 1 plus 0.09 divided by 2 raised to the power of 2 minus 1. Again, I'm going to go directly into Desmos, the scientific calculator, and enter this expression. So open parentheses, 1 plus 0.09 divided by 2 raised, so then close parentheses, raised to the power of 2 using the caret symbol. I push over to get out of the exponent and then put minus 1. And the value that I get back for the effective annual yield is 0.092025. And as a decimal, as a percent, that's 9.2025%. So which account is better? So clearly the 9% account. And the reason for that, it has the greater of the two effective annual yields. It means this one's going to make you more interest over time than this one. So this is the better investment or better account. And that might not be obvious. I mean, sure, this interest rate is lower, but you are compounding more times. Maybe that would make up for the fact that this has a higher interest rate, but compounded fewer times. Turns out that's not the case. This is the better account. One final thought for this lesson. If you've taken any calculus before, you've probably encountered the number e, which is approximately 2.71828, and so on. A lot like pi, it is an irrational number, so that means the decimal goes on forever. And this thing shows up in a lot of applications in calculus. So how does this relate to this lesson? Now, interest can be compounded any number of times per year. So we looked at quarterly, monthly, and so on. But it really could be any number, like even 10 million times you could compound interest over the course of the year. The question is, can interest be compounded at every moment throughout the year so there's no gaps? If you compound quarterly, that means at 4 equal intervals, and there's a lot of space in between all those times. If you compound monthly, there's more times you compound, but there's still a little bit of space between those times. The more you compound, the smaller those spaces get. What would it mean if you were to compound some interest rate at every single moment so there were no gaps? If we think about the formula, it's A is equal to P times 1 plus R over N to the NT. In some sense, you could think about the answer to this question as letting N equal infinity. You compound an infinite number of times from the beginning to the end of the year. Unfortunately, in this formula, you can't put infinity in place of n. Infinity is not a real number. But if you take a calculus sequence, you introduce things called limits, where you can let this get bigger and bigger and bigger. It turns out that if you do that, if you let n get larger and larger and larger, this formula becomes A is equal to your principal value times e to the RT, where R is the annual percent interest rate. So this is the best that you can do, compounding at every single moment throughout the year. You can't use this formula to figure that out because you can't let n equal infinity, but the bigger n gets, the closer to this value we get over here. So on your calculator, you might see a button for e, or e with an exponent, and that's why it's there. E represents this number here. So let's try this formula out in example 7. Suppose you invest $1,000 into an account that earns a 4% interest rate and it's compounded continuously. The terminology for compounding the interest so there's no gaps means continuous. What is the value of the account after 5 years? And we will round our answer to the nearest cent. Well, the way this works is the principal is $1,000. The annual interest rate as a decimal is 0.04, but that's it. Everything else gets plugged into this formula. A is equal to 1,000 times e to the 0.04, and we multiply that percent by the number of years, which in this case was 5. T is 5 years. If I simplify this, that's 1,000 times e to the 5 times 0.04 is 0.2. In my calculator, I get the following number, $1,221.40. So there is a way to compound the interest at every single moment, that is to say, continuously. You can't use this formula to do that. You have to use this one here. This is not a proof by any means. If you were to take a calculus class, you can prove where this formula comes from. But for us, we'll just mostly focus on using this formula here.